Welcome everyone to Algebra 2, Chapter 4. We're going to do Section 1 today. Chapter 4, though, we're talking about absolute value. And so Section 1, we're going to be talking about graphing absolute value. And real quick, I want to talk about the general form of an absolute value function or equation. It's going to be y, or f of x, remember they're interchangeable, y and f of x, equals a times the absolute value of x minus h plus k. Now, you might notice this looks very familiar to what we just learned for quadratics last chapter in section 3, where quadratics was f of x is equal to a parenthesis x minus h parenthesis squared plus k. And h, again, was the left to right movement, so how far it was translated left and right. K was how far it was translated up and down, so the vertical movement, and A was our stretch, compress, or reflection as well, okay? So we're going to use a lot of those same things and really going to mean the same things here. So characteristics of an absolute value function. The graph is V-shaped, so instead of being like a U, it's just a direct V. Then the vertex of the graph is going to be wherever H, K is. And then A, that stretch, compress, reflect, is going to act as the slope for the right-hand side. So we see it's like a linear equational line. And it's going to be, on the left side, is just the same thing, but just the opposite, so the negative version of that. So, section 1, we're not going to do the second one, and we actually just talked about number 1 a moment ago. So, the absolute value parent function. So what is a parent function? A parent function is just the normal one without any transformations to it. So it's not moved left to right at all, not stretched, reflected, compressed, or translated up and down at all. So it's just y equals the absolute value of x, or f of x is equal to the absolute value of x, because they're the same thing. So some different points we plug in are like -3, -2, -1, 0, 1, 2, and 3. And those are just some points that will kind of help us see what the graph looks like. So remember, whatever we plug into the absolute value always comes out positive. So if we were to take like y equals the absolute value of -3, we would say the absolute value of that is +3, because absolute value is defined as the distance from 0, and -3 is 3 away from 0. So you put in -3 and you get 3 out. Well, same thing for -2, you get 2 out. -1, you get 1 out. 0, you get 0 out. When you get 1, 2, and 3. Because basically whatever number you put in, you'll get a positive out for absolute value. And now we can go and graph these. So you do -3, -3, -2, -2, comma 2, -1, 1, 0, 0, 1, 1, 2, 2, 3, 3. And we go and graph them, and we notice we get this V-shaped. And our vertex here is 0, 0. That is the point where it changes direction. And it's always either going to be the lowest or highest point, whichever one it has. In this case, it has the lowest point. It does not have a highest point because it goes up forever because of these arrows. All right, so now some vocab again. A transformation changes a graph size, shape, position, or orientation. So it'd be like the reflection, the stretch, compress, anything like that. Whereas a translation shifts a graph horizontally and or vertically. So that's like the up, down, left, right stuff. But it doesn't change the size, shape, or orientation. So it doesn't change how big it is, which way it's facing, any of that stuff. And those are actually the vocab words that we had last chapter as well. So we're going to continue to use those. So characteristics of absolute value functions. So we have the same equation we've seen a few times already. And the graph has the vertex h, k, like we said on the front. It's V-shaped, and it'll open up, so like this way, if a is greater than 0. So if the number in front of the absolute value of x is greater than 0, aka it's a positive. And it opens down, aka it's reflected, like this, if a is less than 0, which would mean that it's a negative number. And it's the same way we knew if it was reflected before when we were talking about in chapter 3. The graph is vertically stretched, so it's made bigger up and down if a is greater than 1 or a is less than negative 1, which are the same qualifications we had last chapter, and similarly, same qualifications for vertically compressed if negative 1 is less than a, which is less than 1, aka a is between those two numbers. So here's an example. So this negative 2 tells us two different things. The negative tells us it opens down. So the negative specifically tells us it opens down, or that it's reflected. They both mean the same thing. The 2 specifically tells us that it is stretched by 2. And this would also mean that it has a slope of both positive and negative 2. Positive 2 for the right side, negative 2 for the left side. And we'll see that in a moment when we start graphing here on the next stuff. This plus 2, we do the opposite for what's with the x, just like before. So that means we're going left 2. We're translating left 2. This minus 1 means that we're going down 1. That one we do exactly what it says. And then the 2 comma negative 1 tell us that the vertex is negative 2 comma negative 1. It's the opposite x, the same y. Just like here, opposite x, same y. So you notice the correlation that, hey, it went left 2, vertex is negative 2. It went down 1, vertex is negative 1. That correlation will always exist. The reason why that correlation always exists is because the vertex would typically be at 0, 0 is where it would typically be. And so whatever translations happen, move the vertex as well. So when every point's moved left 2, the vertex is moved left 2. When every point's moved down 1, the vertex is moved down 1. All right, let's go and turn to graphing these. So graph the following without creating a table. So just using this information. And it says describe the transformation. And it might be easier for us to describe the transformation before we start graphing. That's up to you. So this is a positive a. A is 2, so it opens up. So it's going to look something like that. The 2 says that it's stretched by 2, so the slope is positive and negative 2 for the left and the right side. So that'd be like a 2 over 1, we could also say. The plus 1 means that we translate left 1 because it's the opposite. The minus 4 means that we translate down 4. So now we can go ahead and graph these. And instead of our vertex starting at 0, 0, it's going to be left 1, down 4, aka negative 1, negative 4. And we said it does open up with a slope of 2 over 1. So we go up 2, right 1, or up 2, left 1 for a negative 2 slope for the left side. And connect them, draw the arrows. Boom, we have our graph. And we said the vertex was at negative 1, negative 4. And now that we have it graphed, we can actually tell the x-intercepts a lot easier by looking at the graph and say, hey, where does it cross the x-axis? Crosses it at negative 3 and positive 1. So once again, we pulled all this information from the equation. The positive part of the 2 tells us it opens up. The fact that it's a 2 tells us that's a slope, positive, negative 2. The plus 1 tells us it's translated left 1. The minus 4 tells us it's down 4. So now I would recommend that you try letter B on your own. All right, so letter B, it opens down. The reason we know that is because of this negative. The slope is positive negative 1/2 because of this 1/2 that's being multiplied by. This negative 1, positive 5 tells us it's being translated right 1 because it's -1, you do the opposite, what's with the x, and up 5 because you do the exact same for what's with the y. So we'll go right 1, up 5, and it opens down with a slope of 1 down, 2 right, or 1 down, 2 left. And the vertex would be at 1, 5. All right, now we're supposed to find the equation of the graphs. So we'll want to pull out the same characteristics and say, okay, well, this one opens down. And so we say, okay, what does that mean? Well, we know it's going to be, a is going to be some negative number. We say, hey, what's the slope? Okay, well, the slope goes down 2, left 1, or down 2, right 1. So that means positive -2. So the a is a -2. It's a negative because it opens down, and the 2 comes from the slope. Then we can say, okay, well, where's the vertex? Instead of being at 0, 0, it's 2 to the left, 1 up, or 2 up. So it's translated 2 left and 2 up. So we can use that information, and now we can say, okay, well, f of x or y equals, f of x or y equals, I was making sure I was following the same notation we've been using. Either way, it's fine. Then we'd say, okay, -2 for the a, then you have the absolute value of x minus some h. Well, it's 2 to the left, so that'd be +2 because you want to put the opposite. And then 2 up, we're going to put +2 because we're doing exactly what that one says. And that covers our information. The -2 tells us it opens down with a slope of 2. The +2 and x to the x tells us it's left 2, and the +2 at the end tells us it's up 2. I'd recommend you go ahead and try number 3. On number 3, we can tell it opens up. So a is positive. The slope is up 1 right 3 or up 1 left 3. So the slope is 1/3. So that means a is positive 1/3. It's positive because it opens up. It's 1/3 because of the slope. The vertex got moved, so it got translated 1 left and 2 down. So that means we plug these in accordingly, and we get f of x is equal to 1/3 x, and it went 1 left, so that's +1, and it went 2 down, so that's -2. All right, let's apply it. So here, Science Museum exhibit, beam of light originates at a point 10 feet off the floor. So that's here originating this beam of light. And then it's reflected off a mirror on the floor that's 15 feet from the wall that the light originates from. So 15 feet away from this wall, you see this mirror. Then it reflects off the floor and goes up to the opposite wall, and we're wanting to know how high. So we're wanting to know right here, what's that height is what we're trying to find. And that's 8.5 feet away from where it hits this wall from the mirror. So we're supposed to model it with an absolute value function and using the outline steps. So any points that we can label? Yeah, there's some points we can label. Where the light originates is 0, 10, 0 left to right, 10 up. The vertex would be important. The vertex is over here, 15 feet to the right, and 0 up or down, which, as we know, the vertex, yes, it's 15, 0. And then we want to find all the way over here, so that's 15 plus 8.5, so that's 23.5, comma, whatever that y value is, which we don't know that. So actually I'll erase this and say, hey, this is the y value we want to find. So now can we find the slope using the points we know? Yeah, we totally can. So we can use these 2 points and do, so m equals y2 minus y1 over x2 minus x1, and we can get 10 minus 0, 0 minus 15, we get 10 over negative 15, which reduces to negative 2 over 3. And so that'd be really a positive negative 2 over 3 because it's a negative on this side, a positive on this side. So now we can write an equation, and we can make sure our vertex is our starting point. So our equation is going to be y, or f of x, equals 2/3, because that's the slope, and it's not opening down, so it's positive, x, and then we went 15 to the right for our vertex where our mirror is, so that's minus 15, and we didn't go up or down at all, so we don't need to put anything, so we can put plus 0, but we don't need to. So that's our equation. And now we plug in the appropriate x value to solve for the height. So we want to know the height 23.5 feet away from the wall, because the 15 feet to get to the mirror, the 8.5 feet to get to from the mirror to the other wall. So we take this equation, y equals 2/3 times the absolute value, let me try that again, 2/3 times the absolute value of x minus 15, and we put in 23.5 minus 15. And we start solving. So we say, okay, y equals 2/3 times the absolute value of 8.5. Then we say, okay, well, the absolute value of 8.5 is 8.5. So we do 2/3 times that, and we get y to be approximately, and let's go to the nearest hundredth, so that's 2 decimal places, 5.67 feet. So how high up the wall does it reflect? 5.67 feet. So we use the points it gave in order to make sure that, hey, we can write an equation by finding the slope and the vertex. So if you know the slope and the vertex, you can find the equation. Then we were able to plug in whatever x value we wanted to figure out a y value. All right, that